So we are now going to move to the next speaker for the plenary session, which is the Professor Dr. John Wang. Before we listen to his talk, let me first read his brief biography. John Wang is a professor of material science and engineering at the National University of Singapore, NUS. He has more than 30 years of experience in research and education of functional materials and materials chemistry. After obtaining his Ph.D., he served as the head of the Department of Material Science and Engineering at NUS for 7 years, from 2012 to 2019. His current research focuses include energy materials and devices, 2D materials chemistry, and nanostructures materials for energy and water technologies. He has published more than 500 papers in prestigious top international refereed journals. And his H index is 84. In 2019, Professor John Wang is elected academician of the Asia Pacific Academy of Materials, APAM. John Wang is clarified Web of Science highly cited researcher in 2020. In this conference, Professor Dr. John Wang will deliver a presentation entitled Electrocatalysts from Nano to Single Atoms. Professor John Wang has prepared a pre-recorded video of his presentation. So let us listen to what he has to say.
I thank the organizer for giving me the opportunity to give the talk today. My talk is on electrocatalysis from nano to single atoms. My name is John Wang. I'm from the National University of Singapore. There has been a steady evolution for catalysts from particles to nanoparticles, then to clusters. Now we come to the single atoms. So if you look at the change from bulk to nano to subnano to single atoms, we have a steady increase in the energy level. So this is a good parameter for the catalytic applications. We can change a bulk material such as a 3D nanoparticle to 2D to 1D and eventually to single atoms. The idea of the single atoms can be dated back to something like 20 or 30 years ago. So this was a study people did about 25 or 30 years ago by putting gold single atoms on the substrate of TiO2. So if you look at the advantage for the single atom catalyst, they can have a higher activity. We can make use of every single atoms if we are going to put everything on the surface. So therefore, we can reduce the metal loading and therefore reduce the cost. We can also have a higher selectivity because each of the single atomic species, they can be selective to some specific reactions. This would be useful for some complicated reactions, such as the CO2 reduction. In the CO2 reduction, we can have various pathways to different products. In any of the pathways, we can also have the different steps. So therefore, the selectivity is very important for some of the catalytic reactions. The catalyst, including the single atom catalyst or the nano catalyst, they have wide applications. anything from oxygen reduction reaction to batteries to nitrogen reduction reaction to OER, HER, or the CO2 reduction, or the applications in the fuel cells. Over the past 5 or 10 years, there has been a steady transition from those noble metals for catalytic applications, because those noble metals, they are high cost. So therefore, in nowadays, we're trying to explore the transition metal for the substitution of the noble metals. A good example here is the cobalt. We can make a cobalt into various compounds. We can also make a cobalt into the single atomic species uploaded on a particular substrate. I'm going to give you some examples later on. One of the very useful substrate for the catalytic support or the catalyst support is the carbon-based materials, especially the nitrogen-doped carbons. By doping nitrogen in, we can make the carbon substrate become more reactive in order to load up some of the atomic species on the surface of the carbon-based substrate for catalytic application. Now I'm going to give you some examples on the single atom catalyst, what we have done over the past few years. Before I give the specific examples, I'm going to mention if we are going to put any atomic species, the story is very complicated because we can have different locations on a substrate surface. As what you can see, we can have a corner, edge, vacancy, etc. So therefore, the story is very complicated. If we are going to put some of the atomic species, we can also have a various bonding coordination environment, different, from location to location. So therefore, effectively, we should define if we are going to put up some atomic species on the surface, we are going to form a surface hetero compound, because the single atoms, they are not going to stay as singles. They are going to form bond and coordination with the substrate. They are going to form a kind of what? The surface compound. We also must understand the compound can vary from one location to the other depending on where are the atomic species on the surface. So that's why we define them as the surface hetero compounds. If I'm going to give you one example, if we are going to put some copper atomic species for nitrogen reduction reaction, if we are going to use the nitrogen doped carbon as the substrate, we are going to form the bond between copper and nitrogen. So the notation of the formula for the compound on the surface is copper in X. This number of the X here can vary from anything below 2 to more than 4 here. So that's why I said we are going to form a series of the surface hetero compound if we are going to put some atomic species on the surface. So if I'm going to translate the figure in this table, what you can see, we have a varying nitrogen to copper ratio if we are going to put some copper single atoms on the surface of the nitrogen doped carbon substrate. In order to prepare the single atoms, we can have two categories of the techniques. The first category of technique here is the additive type here. Means what? We can put up the atomic species on the surface of the substrate by different techniques, by deposition, precipitation, reaction, etc. The other category of the preparation techniques is the subtractive type. Generally speaking, by the subtractive processing techniques, we prepare a precursor in different forms. After that, we are going to convert the precursor into the structure, into the material we want by temperature, by ionic change, or by the other conditions in order to convert the precursors into the material, into the catalytic materials we want for a particular application. One of the very useful precursor to make the atoms, single atom catalyst, are the MOFs. MOF are the metal organic frameworks. There is a very big family of the metal organic framework. So if we look at those MOFs here, they have everything we want for preparation of the nanomaterials or the single atoms materials for catalytic applications. We have a carbon, common metal salt with some organic linkers. We are going to control the condition in such a way we can form a 2D structure. So after forming the 2D structure, we can convert the 2D structure into a substrate with the atomic species on the surface by a kind of thermal annealing. So in such a way, we can make the heterogeneous catalytic species on the surface of the substrate. So this is a very common procedure in preparation of the heterogeneous catalytic materials. In reality, we can prepare very different materials if we are going to choose a proper salt, organic linker, or some of the direct agent. We can form different materials or different structures on top of the nitrogen doped carbon. We can form any other compound such as the phosphate here. So therefore, we can extend the preparation process into very different materials. So now I'm going to just give you one example how we can prepare the cobalt single atoms on the substrate of the nitrogen doped carbon. We choose MOF here. We can grow the cobalt MOF. We are going to form a two-dimensional MOF structure on the surface of the carbon fibers or carbon cloth. So after that, we are going to convert MOF into nitrogen doped carbon. On the surface of the nitrogen doped carbon, we have the cobalt atomic species. At the same time, we also have some of the clusters of particles due to the aggregation of the cobalt metal selectivity towards the nitrogen reduction reaction towards the hydrogen evolution reaction. Actually, these are the two competing processes in the nitrogen reduction reaction process. We always have a HER to compete with this process. The question is, if we are going to combine the single atoms with crystals, with nanoparticles together, whether we can speed up one of them at the same time, we can depress the other one. So therefore, we have prepared a electrocatalyst consisting of the carbon nanoparticles at the same time on the same carbon nanotube. Here, nanotubes are acting as a kind of substrate. we have also uploaded some molybdenum single atomic species. So therefore, in such a way, we are going to combine the nanoparticles and the single atomic species together. So if we are going to look at the performance by the combination between the single atoms and the nanocrystal for the nitrogen reduction reaction, the performance is really much better to have single atomic species or nanoparticles or nanomaterials. We needed to put up the active species on the surface of the substrate. So if we are going to bury them below the surface, they are not going to do the work for the catalytic reaction. Also, as what I have said, the single atoms are not singles. They are bound. They are coordinated on the surface to form a specific chemical bond with the substrate. That's why I have said single atoms are not singles. We can also have the beyond single atom catalyst. We can have the metal dimer or trimer. If we are going to combine the two together in a specific configuration, they can be much better for some catalytic reactions. We can also have the story. If we are going to put a few of the atoms together in group, they can also be much better for some of the reactions. I'm going to thank my team here. They have been working very hard to produce the results which I have presented today. I also have the collaborators such as Professor Penny Cook, Professor Tony Cheating, also Dr. Sinley. Also, I thank my founding grantor in Singapore to support my research. Thank you very much. Thank you.
Okay, thank you for Professor Dr. John Wang for that presentation. Ladies and gentlemen,